Hi everyone. In this video, we're going to go through section 5.2, the addition rule and complements. Fortunately, this being our first section now that we've kind of transitioned online, this is a fairly brief section. It's not a lot of heavy content, but we'll certainly get to that as we move forward here. We start out with a definition. In probability, when two events are disjoint, they have no outcomes in common. Okay, so another term is they're mutually exclusive. So think if I roll a dice and I spin a spinner, those two events are disjoint. What happens on the die does not affect what happens on the spinner. Okay, and it's often helpful to use Venn diagrams to represent this. Disjoint events or mutually exclusive events are two circles that have no overlapping section. All right, and then when we talk about probabilities for disjoint events, we have the addition rule when we're talking OR statements. The addition rule says that if I take the probability of E or F, of one or the other happening, that is the probability of E plus the probability of F when they are disjoint. Okay, so in this scenario, we have our sample space. In this example, we have our sample space S containing all the digits 0 through 9, and you can check. You got 0, 1, 2 in E, 3, 4, 5, 6, 7 outside in the white space, and 8, 9 in F. Okay, so if I want to know what is the probability of E just by itself, well, I have 1, 2, 3 numbers in E. So what is the probability? There are 3 things in the event E. Okay, so the number of outcomes in event E is 3. The total number of outcomes in the sample space is 10. There's 10 numbers total. 3 numbers in event E, 10 numbers total. The probability of the event F, the event F is, well, the numbers 8 and 9. There's 2 numbers in event F and 10 numbers in the sample space. So the probability of E or F happening is 3 over 10. Plus 2 over 10. Whoops, why did I write 5? 2 over 10 equals 5 over 10. Or I could simplify that to a half, or I could put it in decimal form, 0.5. And that's it. Some of the examples that you'll see will get a little bit more involved in that, but that's the concept at its most basic. When events are disjoint, we add the probabilities together. Okay, moving on to what's called the general addition rule. Now my events are not disjoint. You can see in the picture where my event E and my event F have some overlapping section. The digits 1 and 3 are in both of those events. But if you look at that sample space, we still have all of the digits 0 through 9. Represented. So what they show here, the shaded regions, all of them together, green and purple, they represent E or F. The overlapping section represents E and F. So this overlapping section is E and F. It's the digits 1 and 3 are in both E and F. Okay, the whole graded, shaded green, purple everywhere is E or F. Okay, so the general addition rule says that the probability of E or F is P of E plus P of F, but minus the probability of E and F. And I had that semi-highlighted. I'm going to highlight the rest of it. Minus the probability of E and F. And the reason for that, and we'll see as we go through this little example here, is if I take and write down the probability P of E, right? How many numbers are in the event E? Well, I can count them. 1, 2, 3, 4, 5. 5 out of 10. How many numbers are in the event F? I believe that's also 5. 1, 2, 3, 4, 5. Yep. So that one's also 5 out of 10. Well, if I want the probability of E or F, and I start out just adding 5 over 10 plus 5 over 10, that equals 10 over 10. Well, that doesn't make sense. And the reason that is not correct is I've counted the 1 and the 3, those two numbers, I've counted them twice. They're represented in the 5/10 there and in the 5/10 there. So the purpose and why it's in the formula, minus P of E and F, we take out the double counting. We counted them twice, so we subtracted out once. In this type of simplified example, would it make more sense just to say 1, 2, 3, 4, 5, 6, 7, 8? Of course it would, right? practically, there's many different ways to approach this on a practical sense. But formula-wise, technical definition-wise, we take and add each individual probability, subtract out the overlapping section, and in this case, we're left with 8/10, or 4/5, or 0.8 as our answer for that one. All right, now an example where we're using this general addition rule, but not just with a Venn diagram, is the probability. What is the probability of drawing a king or drawing a diamond out of a deck of cards? Okay, so things to know if you're not familiar with decks of cards is there's 4 kings, and how many diamonds are there? There are 13 diamonds. And there are 52 cards in total. Okay, that's the setup. And so you could look up some things about a deck of cards if you come across it in a homework problem. Go use the internet, look up, familiarize yourself with a deck of cards. But in this case, if I want to know what is the probability of drawing a king or drawing a diamond, well, that's the probability of a king plus the probability of, I'm going to abbreviate diamond to just D, plus the probability of a diamond, and minus the probability of drawing a king and a diamond. Okay, and are there any kings that are diamonds? The answer is absolutely. There's one of them. Okay, so we take our 4 kings out of 52 cards in total, plus 13 diamonds, 52 cards in total, minus 1 out of 52, the king of diamonds, because that king of diamonds, he was counted in the 4 and in the 13. So when you simplify that, 4 plus 13 is 17, minus 1 is 16 out of 52. And that 16 over 52 simplifies to 4 over 13, or in decimal form, this one I'm going to round to, let's say 3 decimal places, 0.308. 3076 rounds to 0.308. Okay, so there's another example where we can apply this general addition rule for probabilities. Okay. One other place where we can take this is to something called a contingency table. A contingency table, it relates 2 different categories of data. So in this example, we're relating the categories of data, the 2 categorical variables. The first one is gender, male and female, going across the top, and then going down the side of the table, we're looking at marital status. What are the marital status of these males and females? And I believe this comes from the population of America some years ago, and it's from the U.S. Census Bureau. Okay, one thing that would be helpful is if we found some totals here. So 40.2 plus 34. So we can make some totals going across because they might come up as you go through this problem. So if I add those 2 numbers, I get 74.2. If I add these 2 numbers, I get 124.2. Add these 2 numbers, I get 14.4. Add these 2, I get 23.8. And these 2 should give me 345.6. Then if you add down the columns, this column you get 117.8, checking your calculator. This column you get 124.4. And then the total overall is 242.2. There we go. And those are technically in millions of people. So that the total population contained within this survey data is 242.2 million people. All right, so now we're going to answer each of these 4 probability questions. Okay, first is A. What is the probability that a male is selected? So essentially we're asking, if I randomly select someone from this population of people, someone in the U.S. in whatever year this was taken, what is the probability that that person is male? Okay, so P of male is equal to, well, the males are represented by the 117.8 number, so that's 117.8 over the total population, 242.2. All right, and if you check that in your calculator, let me type this in real quick. 117.8, 242.2. As long as I type that in correctly, I got 0.486, or I could write that in percent form, 48.6%. So there's a 48.6% chance that a male is selected out of this population. And an important thing to note is, and I'm going to highlight it too, that probability question always refers to the population represented within this problem, within this sample space. Okay, so for part B, what is the probability that someone is randomly selected and they are widowed? Widowed. There we go. So what I need to do is find the number that are widowed, which they're represented by the 3 and the 11.4, which is 14.4 over 242.2, because that is the population in this problem. So I'm going to type that into my calculator, and let's see what we get. 0.059, because I think I did 3 decimal places. Yep. 0.059, or 5.9%. All right, moving on down a little bit here to part C. Now we get some or questions. What is the probability that someone randomly selected from this population is widowed or divorced? Okay, and now these two events, to use the term from the beginning of the section, these two events are disjoint. There are no individuals represented within this population that are both widowed and divorced. They are mutually exclusive. Okay, so I can take and find what is the probability that they are widowed plus the probability that they are divorced, and not have to worry about any overlapping sections. Okay, so for this one, we've got our 14.4 again over 242.2 plus the divorced, where are they? 23.8 over 242.2. And when I add them up, 14.4, 23.8, I get 38.2 over my denominator. 2, and then checking that guy in my calculator, that's about 15%, no, 16%, 0.158, or 15.8% for part C. Okay, now for this last part, part D, let's move over to the right a little bit so that I can keep my contingency table up there. All right, we'll put part D over here, and this is the one where they're not disjoint. There's overlapping. So in this part D, we want the probability that someone selected from this population is either male or widowed. W-I-D-O-W, there we go, E-D. All right, and the probability that they are widowed, male or widowed, we need the probability that they are male, so P of M, M for male, plus the probability of finding someone widowed, minus the probability that they are male and widowed, because there is an overlapping section. You can find it. It's right here, right there. That's the overlapping, okay? Those 3 million people are both male and widowed. All right, so we fill in our probabilities now. I think we've already used many of these. Male is 117.8 over the 242, plus the probability that they're widowed, that's the 14.4, 242.2, minus the section that I circled, 3 over 242.2. All right, so we can do that addition and subtraction. Plus 14.4 minus 3 is 129.2 over 242.2. And when I do the division in my calculator, I get a probability of about 53%, 0.533, or 53.3%. Okay, so we have an example of individual probabilities, we have an example of disjoint events here, and then an example of this general power rule where we have that overlapping section. Okay, cool. So now moving on to the last topic in the section, and we don't really have an example to go along with it. It's fairly straightforward, though, hopefully. If we have S, our sample space for some probability experiment, and E is the event, then this definition here is for the complement of E. Notation, it's E with a little exponent. It's not an exponent, it's a superscript of capital C. It's all of the outcomes in the sample space that are, and I'm going to highlight this word rather than just circle it, that are not outcomes of the event E. So the complement rule, the formula for it, the P of E complement, probability of E complement, is 1 minus the probability of E. Okay, so visually where that's represented in the sample space is out here. All the stuff in the white represents the complement of E. This, as human beings, we have in built-in understanding of the complement when we talk about probabilities or when we talk about percents. If I told you that there's a 40% chance of rain, you're like, oh, that's a pretty good chance of not rain because that's a 60% chance of not rain. You've just, like, in your head immediately done a complement. You don't call it that, but when I subtract something from 100% to find out the opposite, that's finding the complement. Okay, so this topic will come up within the homework questions, but we're not going to take the time in this video to do an example, an in-depth example of it. Okay, thank you for watching. Let me know if you have questions. Please send me an email if you do. Throw the timestamp on there, and I will try to provide greater clarity if there's something that was unclear. All right, thank you again.